welcome to this section of the course. We'll be discovering some new trigonometric identities. I'm so excited to get started. Let's get to it. So, you should be familiar with our very initial identities that we learned in year 12. They were 1 equals to, or 1 is rather equivalent to sine square theta plus cosec square theta. This is our very original first identity that I proved this to you with from first principles, that if we have a right angle triangle here and we can apply the Pythagoras theorem and come up with this identity. So I'm not going to prove that again here, but okay, so what can we do with it? Now, if we treat it as an equation and say sine square plus cosec square is 1, then we can divide both sides of this every term of this equation with cos square, say. Okay, so what happens when we divide by cos square? We're going to get sine square theta over cos square theta. Cos square divided by cos square is going to be giving us a value of 1, and we will have 1 over cos square theta here. Now, we do know this is tan square of theta. We do know this is a 1, and now from our identities, 1 over cos square can be written as secant square of theta. So there is our very original expression that you can record in your handbook and pass it to your memory. It will be very useful in later sections of the course where we solve trigonometric equations. Now, going back to the original expression that we had, sine square theta plus cos square theta can also be divided by sine square theta. So if we divide every term here by sine square, what we end up with is another expression. Can you tell me what it is? If you like to pause the video and have a go at it. Yes, we'll have 1 here, we'll have cotan here, sorry, that's cotan square here of theta, and on the right side we'll have cosecant square of theta. Alright, so these identities can also be rearranged. So if somehow you need to prove this identity, you can also use the fact that tan theta can be written as secant square theta minus 1. That's one rearrangement of the same equation. And also cotan theta can be written as cosec square of theta minus 1. Alright, going back to these boxes here, actually, we can actually confirm these identities if we consider this shape here and take unit 1 to be the smaller side of the triangle, and look at this right angle here. 1 square plus 10 square. 1 square is still going to be 1. So 1 square plus 10 square will give us secant square as the orange line at the bottom of the screen is showing. And that's just Pythagoras applied to this right angle triangle. And there is another right angle triangle here where the yellow line cotangent square plus 1 square will add up to secant square. There is the Pythagoras applied to that right angle there. Okay, and uh, for fun, you can also have a go and bring up our very famous Desmos calculator, graphic calculator, and play around with this this graph here, where if you type in Desmos calculator and type in this URL, or just type in uh, cotangent, secant, and or cotangent, and with Desmos, you should be able to find this graph where you can change this slider value, and the angle A actually is showing you is changing that. So as I increase angle A to be more and more towards 90 degrees here, or pi over 2, you see the the secant at the bottom of the curve will the secant will become parallel to the to the line or the line, and therefore secant is not defined at 90 degrees. Okay, but anyway, you can play around with this at your own in your own time, and confirm these identities. The right angle uh, identities apply here as well. Okay, so let's go back and check out what we can do to when we were asked to solve some problems using these new identities that we've discovered. Hello again. So let's read this next example. It's told us that tangent of tan of A equals to negative 5 over 12, and the, the fact that it's negative, it's telling us that this angle is actually an obtuse angle. The word obtuse means an angle between 90 and 180 degrees. So to picture this, we will. Uh, Hello, hi. So let's look at this example one more time. So we have an obtuse angle that is between 90 and 180 degrees. The fact that the tangent of this angle is negative 5 over 12 is telling us that this angle is between 90 and 180 degrees. And we've been asked, so let me show you the entire question, to calculate what is the secant of this angle here. So if I just highlight this for you, that secant of A is 1 over cos of this angle. So we need to first of all calculate what this angle A or theta is before we can calculate this cos value. So let's look at this angle here. So if we pretend that we have a unit circle here, actually the angle is somewhere in this region. So the fact that this obtuse means that we are talking about this angle here, and we can find this tan to be negative 5 over 12, like so. So to calculate the cos of this angle, we know that actually this 5 is positive and 12 is negative, because 12 is the x value, and using Pythagoras, you can figure out hypotenuse is 13, is a famous Pythagorean triplets. So the cos of this angle, cos A, is going to be negative 12 over 13, and 1 over cos of this angle is going to be 1 over negative 12 over 13, which is simply negative 13 over 12. So that's the ratio of sec for this example. Let's look at the next example. Right, so one more time, we have the same setup, but this time we've been asked to calculate the cosecant of this angle here. Now, cosecant is 1 over sine of angle A, capital A. And from our previous discussion, we said that this angle is obtuse. That means that it's actually in the second quadrant of the unit circle, and the setup was like so. Therefore, if we read the sine of this angle here, sine is sine is opposite over hypotenuse, which is 5 over 13, and 5 has to be positive in this quadrant because actually it's in the positive part of the y value is positive, and hypotenuse is always positive. Therefore, 1 over 5 over 13 will give us 13 over 5. So let's look at the next example together. Okay, so in this example, we've been asked to prove that cosecant to the power of 4 minus cotangent power of 4 is equivalent to this fraction, which is 1 plus cos square over 1 minus cos square. So what can we do here? Well, I would start from the left-hand side expression over here and write it as 1 over sine to the power of 4 subtracted by cos to the power of 4 over sine to the power of 4 theta, because that's the definition for cotangent, cos over sine. So powers of 4 will be distributed on the top and the bottom. So we can already see that these two fractions have the same denominator already. So we don't have to do a lot of hard work to figure out that we can simply subtract the numerators from each other and only write the denominator once. And now, what do you remember from your year 12 factorization work? Whenever we had difference of two squares, we could factorize that as, for example, a square minus b square would have been factorizable as a minus b multiplied by a plus b. So in our case, we have a power of 4, and we can treat this 1 as 1 to the power of 4. Okay, that's still fine. That's because the powers of even, we can always halve the powers. We can think of a being uh, 1 square. So a square will be 1 to the power of 4. And we can think of b being cos square. So b square would be cos to the power of 4. So we could factorize the numerator as 1 plus cos square theta and 1 minus cos square theta, right? And we can rewrite sine square as sine to the power of 4 as sine square times another sine square, and we know the other. Okay, let me just write it. So this sine square in the bracket can be written as 1 minus cos square of theta, and because we have that in the numerator, it's better to have written that one more time. 1 plus cos square theta, 1 minus cos square theta, all over sine square theta, 1 minus cos square theta, to show that these two brackets cancel each other out. And finally, we can rewrite the sine square in the denominator to be what's in the question on the right hand side in the denominator. So we will have 1 plus cos square theta and 1 minus cos square theta here. So, and that is the right hand side of the expression we were given. So it always helps to write where we start from and where we end up so that we can get our full marks. Okay, so let's look at the next example together. Okay, so looking at this problem, there are many ways to solve these identities and prove them. There is no right or wrong answer as long as you get from one side to the other. But I'm going to start with the left-hand side here, and I can rewrite secant square as using our newly learned identities as 1 plus tan square theta, and write cosecant cos square as 1 minus sine square of theta. Okay, distributing the negative sign into the bracket, I will have 1 plus tan theta minus 1 plus sine square. Now, having done that, we can cancel away these ones. Tan can be written as tan square is sine square over cosine square, and we are going to add sine square to that. What you notice is that we can factorize the sine square out of both of these terms, and inside the bracket, what what we'll end up with is 1 over cos square theta plus 1 simply, because we factorizing sine square, and we can rewrite this as sine square theta. And just to make sure the terms match with each other, I'm going to bring that 1 and write it first inside the bracket, and bring this 1 over cosine and write it as sec square, so that it will exactly match up the right hand side of the expression we were given in the question. Right, so that solves this problem. I'll see you in the next example. Right, let's look at this example together. We have 4 cosecant square theta minus 9 equal to cotan, and we were asked to solve this equation. This is not an identity to prove, so we are to solve and find the angles in terms of degrees. So make sure in the final stage your calculator is in degree mode. Okay, so we have cosec square here, and what we can use is one of our newly learned identities, which I'm underlining on top of the page. So we can write this as 4 open brackets 1 plus cotan squared of the angle theta. Noticing there is only a coefficient of 1 in front of theta, so we don't have to adjust the range there, and subtract 9 from that and write cotan there on the right hand side, cotan of theta, not cos, cotan. Right, so expanding the bracket here, we'll have 4 cotan squared theta, and we can subtract that cotan from the right hand side, bring it to the left, and we end up with an expression which is looking more and more like a quadratic equation. So if I combine the negative 9 and the 4 with each other, we'll have a negative 5, and this you can think of as 4c square minus c minus 5. Now, with your graphic calculator or the quadratic equation, you can factorize this expression into 4 cotan. I'm going to go back to cotan rather than c, minus 5, and the other factor would be simply cotan of theta plus 1. Okay, it's equal to 0. So one of the answers will tell us that cotan of theta is 5 over 4, the other is -1, and therefore tan of theta, taking the reciprocal of the fraction, is 4/5, and tan of this theta will be still -1. So one of the answers here is 38.7, and adding 180 degrees to that, we get 218.7. Now, this angle turns, first of all, your calculator might give you -45, which you can add 100, and it's not usable itself, but adding 180 to it, we can use that value, that is 135, and still add another 180 degrees to it, and we'll end up with yet another useful answer, which is 315 degrees. Okay, so there you go. These four are the final answers that I'm underlining. So with that, I'll end this examples, and I'll see you in the next section.